Okay, thank you, Eric. Good grief. Let's go. Most of that stuff is housekeeping, but let's quickly run through this. So I thought I hit record button. So here we are. This is the 18th. 4 more days to go. Weather, we're looking at possible rain on Friday, rain every day. We'll see about the picnic. I will hand out the packet organizer, but it'll be Friday, not Thursday. Bring a dessert Friday and you get the free food. Eligibility today by 5, and I'm working on new equation sheets. Okay. Table 4. So what I went around today and checked 1 and 2 on the take-home test. And they got a couple stars for that. So that's, like I say, that's the only homework we're going to have from now on. It's just the take-home test 6B. Tomorrow, to keep up, you should try and get 3, 4, 5, and 6. You get 4 stamps. They get 4 stamps, 3, 4, 5, and 6. Come join us. I'll give you stamps. 42 stars so far out of 40. So we've reached what we're trying to get to, our goal. Okay. Like I say, though, from now on, homework is all take home. And Thursday nights, we go over the key. We not the key, we go over it and answer your questions. All right. This is the problem we're working on. We did the number 1, and really you should be able to answer 2, 3, and 4. But 5 is what we did today. We looked at 5 real quick. Remember, 5 is the graph we've been working on, so we didn't do that much work on it. Remember, this just comes up. That's that is, by the way, it was a slope of 1 because of Newton's third law for reaction. This F, the curly F, is the friction force, and then the FA is applied force. Then remember, it has that knob, and then it comes like that. It's chaotic after that. So this is the kinetic region. This is the F sub K region. This is the F sub S region, static versus kinetic. And then we talked about this a lot, like the 6 and 7 talk about draw the microscopic view. That's the peak to trough, peak to peak. So you should be able to finish the front, I think, pretty much with what you already know. Okay, so on the back, we were doing, when the bell rang, so to speak, we were doing number 11. And I kind of left it to you. I said, okay, I quickly threw it all together. But if you'll solve for the normal force back here, we're trying to determine the equation for angle of repose. And the angle of repose, I'll make that yellow, that equation right there. That theta rep equals inverse tangent of mu sub s. Today, we'll look at some application of that. So you get that in terms of mg cosine theta, plug it in, and then we have this equation. And with this guy plugged in, and then if you subtract them, they're equal to 0. That means they're equal to each other. So we end up with this equation. Mg sine theta rep equals mg mu sub s, equals mu sub s times mg cosine theta rep, and then theta rep, not just any old theta, but the angle of repose. And then as you see, bring out the green kill pin. We can kill those common. And so then divide both sides by cosine theta rep, and we have the equation we're looking for. There's 2 ways to write the equation. So we would have tangent of theta rep equals mu sub s, or sometimes you see it this way, theta rep then equals inverse tangent of mu sub s. So that's the 2 ways you see it. Okay, now let's go to number 12. And I made them, we did this together. Okay, so number 12, coefficient of static friction between the ice and the wood is 0.3. Now, this is a good example of where you get sued. If you're an architect and you build this guy's house, say this is in Minnesota, and you build his house, and he wants to be able to walk on it. And so you don't want to make it too steep. So you put a 10-degree, let's say you put a 10-degree angle on it. Then it starts to snow, and that snow builds up on the roof, and the roof collapses. The guy sues you. Now, if you know physics, you can make a heck of a lawyer. You want something to go before you go to law school, get a physics degree, then get a law degree. You're going to be dangerous, because a good lawyer here, he's suing you because his roof collapsed. He says it's your fault. He said, hey, I just made it a 10-degree roof, I said, nope, that's the problem. So he looks it up, the lawyer that knows a little physics. He looks it up. The coefficient of static friction between the ice and the wood is 0.3. So you can look that up in a book. Okay. And then he shows to a judge, you'll probably win. What is the maximum length that the roof can be? Well, first off, what angle, if this is, well, that's kind of secondary, but what angle should the roof be at? Now, you being the architect, you made it at 10 degrees because it looked good, but what angle should it be at? So once the ice builds up, it'll slide down the roof. See what I'm saying? So it reaches the angle of repose. So ice slides. 10 degrees, the ice is not enough, as we'll see, it won't slide. So we say, okay, we want theta rep. Well, theta rep, go back to my equation here. I want what angle I need. Theta rep then is inverse tangent of mu sub s. Well, mu sub s here is 0.3. There are no units. It's a coefficient. Coefficients have no units. 0.30. Okay. So now take your calculator, which I don't know where it is. You got a calculator there. Somebody punch that in right when I need it. I can't find it. What do you get for inverse tangent 0.3? What do you get for theta rep?
16.7.
Okay, so 16.7 degrees. And so this guy's good lawyer says, look, this architect doesn't know what he's doing, because he made that pitch of that roof 10 degrees. Where in Minnesota, we know the snow is going to build up on that roof. And so it collapsed because he should have made the pitch 16.7 degrees. Guess what? You lose. Physics always wins in a court of law. Physics is the ultimate truth. It'll get you out of traffic accidents, tickets, if you can prove by physics that you're correct. But that doesn't answer the question. The question is, okay, if this is 20 feet, and now we know the angle needs to be at least 16.7 as minimum just to get that. I mean, anything above that, I'd probably go, there's that safety factor. I'd probably go like 18 degrees, but minimum 16.7 degrees to get you out of a lawsuit. What should the length of the roof be? What's the maximum it could be if you know that this joist here is 20 feet? So now it's simply right. It's just a little trig. So there's your right triangle. This is 20 feet. And this angle is 16.7. And the question is, what is my S? So as you know, that's cosine, right? So cosine 16.7 equals 20 feet over S. You punch it in, it's like 20.7, somewhere in there, so around 21 feet. It's probably 20.7 is about what you want there, I think. So that would help you in your architecture days. I know some of you want to be architects. I had a student just graduated in architecture. He started off architecture engineering, and then the engineering was killing him. So he switched just to architecture. The problem with that is, that's great, and he'll get a job probably, but he'll get a kind of a AutoCAD sort of entry-level job. You know, architects don't make much money. $35,000 a year is typical starting salary, I think, around there. You can look it up, but architectural engineers, on the other hand, start off at about $70,000 a year. So it's worth suffering through those hard engineering courses. Anyway, let's go. Now that I sent them to the board to do number 13 to the board. And so for you all, I'll put it on pause, and you all will go to the proverbial board and try and do number 13 on your own. All right, so I'm going to put it on pause. We'll come back in a minute. Well, I'm not going to apologize. Sorry, not sorry, but that 65 pounds was a red herring, not needed. I don't normally do that to you, and I'm not going to do it to you on a test, but you got to get used to it, because in AP physics and in college physics, they give you all this extra information you don't need. And half the problem is figuring out what I need and what I don't need. I figure in an introductory physics class like this, it's hard enough to try and work the problem rather than have to fight through all this extraneous information. Well, anyway, that one wasn't needed because it says this key phrase here, this otter is just about to slip. Just about to slip. That means when you read that, I promise you, in any kind of problem, that means theta rep. That's that catchphrase, just about to slip. So you're going to do theta rep, and it says, what is the coefficient of static friction? Well, the problem's really simple then. The tan of theta rep, and it says 35 degrees, is mu sub s. So all you got to do, hit tan 35 on your calculator. That's your answer. Tricky. We're going to come back to 14 tomorrow. We may get started on that one in the hour. Let's leave that alone for now. Okay. I want to quickly knock off 6-9 because we're going to skip a bunch of it. 6-9, some of this we've done, some of this we're just not going to have time to do. So for number 1, it's a great demo. It's a great thing to do, but it takes the entire hour. One of my favorites, but we just don't have time. So skip that. Maybe. Put a big skip on that. Oh, I hate doing that. It's really awesome. I have video. Maybe I'll put, I'll tell you what, I'll add the video of that just for funsies. I'll put a note to myself. ASCII. Add video of me explaining that one. Okay. Number 2. Now, number 2, I went to a big to-do in class, and I do have, and add video to that too. I have this on video, and I had a kid about 10 years ago that was failing. He had like a 50%. He wasn't like totally failing, but he really wanted to pass the class, and he was a welder. He took welding at Moore Norman, and so I said, okay. Is there anything I can do? Anything I can do? He's desperate. I said, okay, I want you to build me a cannon out of metal that I can use to demonstrate Newton's third law. And he did. He built me a great solid cannon. The problem is, I can't show. I don't have it with me. I can't show it to you. But the problem is, the cannon he built looks like this. It's got a stopcock right there because it's a nitrogen cannon. And then it has a big piece of metal there, and then it's on wheels. So he did what I asked him to do, and I should have been more specific. And then I found a really good stopper. Went up, looked around for this thing for about a month. Finally found me a great stopper. Just put it in there. And then what you do is you pour liquid nitrogen. First, take the stopper out. You pour liquid nitrogen into the barrel. And then you put this stopper on. You hammer the stopper in, and then all of that liquid nitrogen is coming out the stopcock. You shut that valve, and then it builds up all this pressure. Now, in my room, I should have taken a picture of it, but there is a Dr. Pepper plastic bottle stuck in the ceiling. And we had done this experiment one year where we filled it full of liquid nitrogen. We capped it off. We had it nailed down to some wood. We all kind of backed off thinking it would explode. And it wasn't, nothing happened for a little bit. So, a little bit, I mean like 15 seconds. So a kid stuck his head over the top of it. And Bill Fix, who was another teacher there, he grabbed the kid by the scruff of the neck and yanked him back. And the second he did that, that Coke bottle, that Dr. Pepper bottle went flying in and slammed. We still have it. It's still hanging from the ceiling. A lot of pressure builds up. It's called vapor pressure. Liquid nitrogen has got a tremendous amount of vapor pressure. As you know, you can put it in liquid form in high pressure. And I always get the liquid nitrogen from OU. You get these big Dewar flasks you have to bring it back with. So when we pour it into the cannon, the idea was this stopper would come flying out, and then like projectile motion, bop, 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 right? And then we would have our delta X. We would have our, we could then determine the V naught from using kinematics, using projectile motion, type 2B projectile motion. And then we know the mass, the stopper. Then we would have a momentum. And then therefore the momentum of the cannon going backwards would be the same. Well, why didn't this work? Why did I get that stopper did not come? I thought it was going to come off, hit the ceiling. It just kind of came out and poop. It didn't make a big loud noise like I was hoping. But we did it in the hallway. But why didn't the cannon go flying back with pretty good? Anybody see why? Anybody see the problem? It's a design flaw. That it's my fault for not being more specific at how I wanted to build it. Anybody see where most of the energy went?
Is it to the wheel?
Yeah, the cannon, when you look at the so initially, remember it's all about initially. The hold on, let's make it blue. Initially, the stopper comes out, thicken that up a little bit. The stopper comes out with a velocity, right? An MV. Well, the cannon then has got to come back with the same momentum. That's conservation momentum. The problem is it's directed into the ground. And so the normal force increases. If we had put this on a scale, we might have been okay. But if everybody else wants to build this, say you're a junior and I'll have you next year or whatever, or a sophomore, then when you build it next time, we're going to build it at like 1 or 2 degrees. And this demonstration that I have, and it'll look like this. And the wheels he had were too much friction on them. So we'll put ball bearings, good wheels, and then we'll make it decent data. So anyway, that was that one. I'll put the video in the I'll find that video and I'll put it in the comments. Now I send them to the board again to do number 3 today. So I want you to finish number 3. We're going to pause it again, and you're going to go to the board and try and finish the graph on number 3. The graph is supposed to indicate or supposed to represent Newton's third law. Okay, so I'm going to pause it. And then if you're watching this recording, try number 3 on this sheet. Pause. So let's see what you did. When they go to the board, they have the advantage that I don't say a thing. I mean, I try and I force them to work together. And they were, by the time, after about 5 minutes, they all had it right because somebody would figure it out, then all the rest would follow. Anyway, so this should look like this right here. It's just a mirror image, right? If you did that, bravo to you. It's a mirror image because it's Newton's third law. Newton's third law, body A, body B. And so then you need to show it as, and don't need to get a ruler or anything. You show it as force of B on A. And someone said, well, shouldn't that be negative? I'm not going to count off if you make it negative, but it doesn't need to be negative because it's already in the 4th quadrant. The graph in an equation, you got to show it as negative because there's no other ways to show it. But if it's a free body diagram or a graph, you'll see it. It's in the 4th quadrant. It's negative. Okay, 4 we've already talked about, and that was a thing. A fly puts the same amount of force on a truck as a truck on a fly. That always throws people, but it's true. The difference is the fly's got a little bit of mass and therefore is going to have a huge amount of acceleration. We talked about this last week. Whereas a truck has a huge amount of mass and therefore only going to have a teeny tiny bit of acceleration, which is going to be in the order of nanometers per second. So it's not going to notice it. And then we talked about this one already. That was Felix skydiving from a gondola or you off a plane. But the advantage of doing to Felix is up when he first jumped out, there was no air drag. So you don't have to worry about that. And then the earth pulls him down. And then shockingly, we found out that he is pulling the earth up to him. And those are congruent. That shows Newton's third law. Boom. Now we get to number 6. And this is okay. So let me tell you a quick story of Konstantin. Konstantin's a friend of mine now. He lives out in Los Angeles. He's a computer programmer out there, makes good money. Always drives his ninja motorcycle everywhere. He's probably, what is he now, 40, 45? Anyway, so when Konstantin first came to my classroom, he was a little 9th grader. He's from Russia. He didn't say a word. He got there late, like in September sometime. And then he was this little scrawny kid with a little mullet. He just sat there in a classroom full of mostly seniors back then, seniors and a few juniors. And here's a little freshman in physics. And we're kind of laughing about that. So what are you doing in physics? And so he sat back, he didn't say a word, right? He didn't say a word in September or October. And finally, about mid-November, he raises his hand. And we all kind of thought he was deaf or mute or special. We didn't know what was going on with Konstantin. And then he raises his hand. It's like everybody gets quiet. And I look, oh my gosh, Konstantin has a question. And so I've been working this problem, number 6 there. This is where it comes in. I've been working this problem using F equals MA, then doing kinematics and finding acceleration, then doing kinematics, then doing delta. Oh my God. So it took me, I think I spent 25 minutes on it. And Konstantin finally raised his hand, and I said, "Yeah, Konstantin, you speak." And he said, "Your explanation is idiotic." And I thought, "What? What are you talking?" This is a kid come in here and talk to me about. And so then he explained it. He said in Russia, and through broken English, he said we do not do it that way. So the Russia way of doing this is they use Newton's first law, not Newton's second law and Newton's third law. They attack it to use Newton's first law, which basically comes down to a formula called center of mass. So you have x center of mass equals the summation of xi mi divided by the total mass. That little crazy m means total mass. And so you solve it like it's some kind of teeter-totter. Like if you have a teeter-totter and you move around the teeter-totter, like if you move in, your partner is going to have to move in too, right? Now, if your partner weighs, this is torque as well, your partner weighs 3 times what you weigh, and you want that teeter-totter to stay level, the partner's got to be closer into the fulcrum than you do, right? Same idea here with Joe Dynamo pulling on this seal. If you call the whole thing one system, and that's what, by the way, that's what number 1's talking about. So since Konstantin, I had him many, many years ago, I've developed his method, the Russian method. And he solved that problem, which I was 25 minutes working on it. He solved it in like 2 minutes. And we called that the Konstantin shortcut for a long time. And then in AP physics, so then he finished out the year, he started understanding English, then he just totally dominated everybody, every test, ace. And he ended up in the Hall of Fame, of course. He aced the final. Next year, he took AP physics with me, mechanics. By that time, he was in my robotics team. We kind of become friends, and he has this caustic personality, but I respected him, and now we're good buddies. But he's the only guy that got a robot that in a contest caught a robot on fire because of his method. But the next year, he took AP physics, mechanics, aced the test. On his own, he studied E&M, aced it, got a 5 on both as a sophomore. I have seniors that worked their butt off to get a 4 on the E&M. He got it as a 5 studying on his own. So I asked him once, we're sitting around like 11:30 at night after a bop ball. He was a senior at the time, one of my leaders. And at that time we were good buddies. I said, Konstantin, if you're so damn smart, how the heck didn't Russia just kick our butt in the Cold War? Kicked American butt. Your levels ahead of anybody else. He said, because Russia's full of idiots. Anyway, he had been in a special school. He was a troublemaker. They kicked him out because he's bored. His dad came over here to teach at OU. He's a brilliant man, and Konstantin with him. Went to Kent State, blew him away. So he's one of my top 5 physics students of all time. I've had like 5,000. He's one of the top 5. I had to throw my Konstantin story in there. And then when he took AP physics, he developed 2 or 3 other shortcuts that were brilliant that we still use today. They're called Konstantin shortcuts. Russian way. Oh, by the way, now you can work number 10 on the take-home test. That's a 5-second problem. And it's just the same thing we did earlier. Now, the last thing I want to do is number 12 on the take-home test. Pretty much the entire back, the last third side of the take-home test, we'll end up working together. If not, it'll be, well, for them, it's stamps. But okay, so what we're going to do here, the last thing here is we're going to go from conservation of momentum to Newton's third law. Well, guess we came up with both of them. Newton, to me, sort of double dipped here because we're going to show that they're the same thing. All right. Newton manipulated a little bit, then threw his name on it and say, yeah, that's my third law. Yeah. When really he'd already gotten credit for it on conservation of momentum. That's marketing, right? That's brilliant. So we're going to show how to get from this. And I have a way to do it, which in first hour, we found a faster way, but here's my way. I'll give you a quick glance at it. Whoa, it's awful. Yeah. Ooh, that stinks. Let's talk about this. I'm just going to show you. It can get complicated, but I'm going to do a faster way. We're going to do it in four quick steps. Number 12. Now, this could be the derivation on the test, or it could be the derivation of the angle of repose. One of those two. But guess what? No one's listening, but between you and me, you get to use your notes. So mainly what I'm checking for is, did you write it down in your notes? Oh, but I forgot to tell them this. Remember I said on your notes, you cannot take pictures of the take-home test and put it in your notes. But 3 or 4 years ago, the students talked me into this one. You can take pictures of your worksheets, completed worksheets, and put those in your notes. You just can't put a picture of any test and put it in your notes, but any worksheet is legal. Okay. If you want to get notes from somebody else and copy that, I put that in your notes. That's legal. Just cannot be a test. You can handwrite the test though. That's legal. I mean, I'm trying to give you points for preparing. Okay, so we can see that we got to get to force from momentum. So probably the first thing to do, let's expand this. When you see that summation of, let's go and expand this out. So we have P, I think I'll do this in blue. No, I'll do it in black. We have PA, the summation of, right? So we have PAI plus PBI equals PAF plus PBF. These should have little arrows on them to be sure. It really shows you the force. If it's a vector, that theoretically should have an arrow above it. People don't do it. You get lazy. Okay, now I'm trying to get it down to that form. Okay, let's introduce this. That's like an expansion. Then let's introduce, excuse me, Newton's original second law, which is F equals, not F equals ma, it's F, let's say F of force of A on B is going to put a change of momentum. If A acts on B, it's going to change the momentum of B in an amount of time. And so force of A on B is the change delta B divided by T. If you leave out your arrows, I'm not going to count off. And by the same token, the force of B on A, if force B acts on body A, it will change A's momentum through time. Okay, that's just Newton's second law. Well, now what's my next move? What do you think? Next move here.
We don't have to open up the momentum vector, do we?
I did that, and that just, all that does is complicate it. It's not necessary. When I solved it a couple of years ago, we didn't get to this last year because of COVID, but a couple of years ago, I did open it up. And that's what I would say, when in doubt, open up all suitcases. But all that, that doesn't hurt. It just adds steps to the routine. So instead, let me get these up here in the form of, let me get this equation in the form of delta P. Okay, so I'm going to rewrite this as P, okay, P A, I'll get the A's on one side and the B's on the other. So PAI minus PA final equals PB final, careful here, minus PB initial. When Bab does rocketry, he derives this formula every year. It's a big rocketry. It's like a necessary when you're doing rocketry. Okay, so all I did was I rearranged that equation up there. Now, can I divide by time? Is it safe to divide by time? Just randomly divide both sides by time? Is that safe? It is safe and legal if you assume time is not zero. Now, you cannot divide by zero. But if you assume time is not zero in any kind of collision, there is some time involved. It might be a picosecond, but there is some type of time involved. So if I divide this both sides by t, you go, what are you doing? Why are you doing that? Well, you'll see. If I divide both sides by t, that's legal as long as there is some kind of time. Now what do I do?
You substitute the force ones, or
Right.
like you set them equal to each other.
Right. So now I'm going to go ahead and say, let's go with that force thing. That essentially isn't this, okay, this equation here, isn't this, but that's the opposite of delta PA over T. And this is delta PB over T, right? Because it's a change means final minus initial. So equals, that's an equal sign, not minus, equals. And now I can do a substitute where delta P over T is the force sub it in, the force of A on B. And this is the opposite of the force of B on A, which is pretty much what I said. In fact, that is what I said. I just got to change the order. And voila, it is proven. So there's your derivation. And we caught Newton red-handed. He was double dipping there, getting credit for two things when it's really just one idea. But nobody caught it. Where you go? What are you going to question Newton? You saw what happened to Leibniz. You saw what happened to Robert Hooke and many others, Christian Huygens, many others along the way that were just destroyed by Newton. Okay. Yeah, so that does those two. I think we're done. We finished up 6-9. Tomorrow we'll knock on the door of 6-10. Remember the homework to keep up. You're going to do 3, 4, 5, 6 on the take-home test. We'll knock on the door of 6-10. We'll do a little bit of 6-10. We'll do 6-11. I don't see us. 6-11 we'll spend the most of the time on. I don't see us getting to 6-12, but we might, maybe on Monday, a little bit. Definitely won't get to 6-13. So if you want on your packet, you can take 6-13, 6-14, 6-15 and pull it off the back. Now, if you're going to do my June course, we will hit those. If you don't do June, you're going to be a bit of a disadvantage next year. I don't know. I mean, I am recording the sessions, but I'm making them private because people are paying money for it. So, so I don't know. Haven't decided yet what I'm going to do with those recordings. All right. So I guess let's stop the sharing. We're done, and you can stick around, ask questions, or I'll see you tomorrow. No IO today.